Then I'd like to explain the gas drag laws. So we use the three assumptions. First assumption is a particle with rigid spheres. Second assumption is we don't consider the gravity of particles. Third assumption is the momentum of gas is transferred to particles after a collision. We consider the density of gas of the law is approaching to the solid particle with a relative velocity of the gas with u. The mass of the particle is a lower case of the m, and the radius of a particle is expressed r sub p. Momentum flux can be expressed. Rho u is a momentum. Cross-section of the solid particle can be calculated. Pi r sub p squares. We need to multiply the u because the inside of this cylinder is approaching to the solid particles. And by multiplying the rho, you can find out how much mass is included in these cylinders. Then this mass has a velocity of the u. This momentum is transferred to solid particles. Then gas drag law is expressed 1 over 2 coefficient of the c sub d times pi r p square times rho u squares. This is a product of the momentum flux times area. C sub d is called the drag coefficient. It is a function of the some non-dimensional values such as Knudsen number and Reynolds numbers. Knudsen number is defined as a ratio of mean free path of gas molecules to the radius of the particles. Lower case of the L is a mean free path of gas molecules, and R sub p is the radius of the particles. The K is defined as L over R sub p. In Hayashi model, we can easily calculate mean free path of the gas molecule as 1 over n is the number density of the hydrogen molecules times the cross-section for collision of the hydrogen molecules. It is calculated at 3 centimeters at 1 AUs. So this is a mean free path of the gas molecules. If the particles has a radius larger than 3 centimeters at 1 AUs, Knudsen numbers becomes smaller than 1. In that case, gas acts as a fluid because before the collision with solid particles, gas particles frequently collide with another gas molecules. If the size of the solid particle is smaller than the 3 centimeters, gas acts as particles because the gas directly collides with solid particles before colliding with another gas molecules. Then we'd like to also introduce another non-dimensional values of the Reynolds numbers. Reynolds number is defined as a ratio of the product of the gas velocity and the radius of the particles to the kinematic viscosities. So R Reynolds number is equal to the U times R sub P over nu, and nu is expressed eta over rho. So if you consider whether the equation is expressed rho times round V sub I round T plus V sub K round V sub I over round X sub K equal first term in the right hand side is a pressure gradient minus round P round X plus eta Laplace V sub I. We make an order of estimate. Then second term to the left hand side is expressed rho u square over R sub p. In the second term in the right hand side is a viscous term is expressed u over R sub p squares. Then if you take a ratio of the second term of the left hand side and the second term of the right hand side is a rho u squares over R sub p over eta u R sub p squares. This is exactly equal to the Reynolds numbers. If the Reynolds number is larger than 1, viscous term becomes minus compared with the second term on the left hand side. In this case, we can treat the gas as an ideal fluid. We can ignore effect of viscosities. But if the Reynolds number is smaller than 1, then we can treat the gas as a viscous fluid because viscosity plays a crucial role to determine velocity profiles around the solid particles. Then we'd like to calculate the Reynolds number in Hayashi model. The kinematic viscosity can be calculated 1 over 3 times the sound speed of c times the mean free path. Then it becomes a 1.3 times 10 to 5 square centimeter over second at 1 AU. The relative velocity between the gas and the particle can be calculated 1 over 2 eta v sub ks. Then you can substitute these values to calculate the Reynolds numbers. It becomes a 1 when the r sub b equal to the 20 centimeters. If the radius of the solid particle becomes larger than the 20 centimeters, Reynolds number becomes larger than 1. If the radius of the solid particle is smaller than the 20 centimeters, Reynolds number becomes less than 1. Then character of gas is depending on the size of the solid particles. Knudsen number equal 1 correspond to the r sub b equal 3 centimeters. If the Knudsen number is larger than 1, size of the particle is smaller than 3 centimeters, then we can treat the gas molecules as particles. When the solid particle is larger than the 3 centimeters, then Knudsen number becomes less than 1. Then we treat the gas in the disk as a fluid. When the solid particle has a radius of the 20 centimeters in radius, this corresponds to the Reynolds number equal to the 1. The radius of the solid particle is larger than 20 centimeters. Reynolds number is larger than 1. We treat a fluid as ideal gas. When the size of the solid particle is less than 20 centimeters, Reynolds number is less than 1. So we have to treat a gas as a viscous fluid. So depending on the size of the solid particles, we have to use a different gas drag laws because a gas behaves like sometimes a particle, sometimes a viscous fluid, sometimes ideal fluid. At first, we'd like to consider the regime 1, Epstein laws. In this case, gas behave like particles. So gas molecules has a relative velocity of the u. Gas molecules actually moving with a sound speed. All the particles inside of the cylinders can hit the solid particle. The height of the cylinder can be obtained c plus u. The relative speed with respect to the gas to the solid particle is expressed c plus u. The areas can be calculated pi r sub b squares. The momentum transferred from the gas to the solid particles can be calculated r sub b square times rho times c plus u squares. So you could consider that in this cylinders can hit the particles from the behind. Height of the cylinder is expressed c minus u. And the velocity of the gas molecule has a c minus u. And the transferred momentums from the gas molecule to the solid particles is expressed this one. In this case, the momentums has the opposite direction. You need to multiply the negative sign. Then if you calculate this number, it becomes 4 pi r sub b square times rho cu. This is drag force acting on the solid particles when the size of the solid particle is smaller than 3 centimeters at 1 AU. In this case, we don't consider the spherical shapes. But if you consider the spherical shape of a solid particle, you need to divide it by the 3's. Then drag force becomes this expression. Then we need to consider the region 3's, ideal fluid. We don't take into account the viscosity of a fluid. Inside of these cylinders can directly collide with solid particles. This is U. Momentum of each single hydrogen molecule can be calculated. Mass of the gas molecule times U is the momentum of a single gas molecule times pi r sub p squares times n sub hu. So this corresponds to the volumes times number density. Give us the how many gas molecules can collide with the solid particles. Then you can express the pi r sub p square times rho u squares. This is the drag laws for the particles with a size larger than 20 centimeters. Last one, regime 2. A velocity profile of fluid is significantly modified within the boundary layer of a solid particles. Instead of the geometrical radius of a solid particles, it is better to use the width of boundary layer of a solid particles. Width of the boundary layer of the delta can be calculated with this equation. So when Reynolds number equal to the ones, delta is turned to be radius of a solid particle of the R sub b. So instead of R sub b, you need to substitute the boundary layers. The drag law is expressed R sub b squared times rho u squared divided by R, Reynolds numbers. This is the drag laws of the Stokes laws. So I explained the drag law in this first section. This is the end of the first section.